Okay, so we are going to look at some sample problems for third period math applications. So this isn't really covered too much in your ILM, but I'm going to start a little bit from the beginning here. Series resistive circuits, just for a review. So the three things: one path for current, the total resistance is added directly, and the voltage drops must equal the voltage rises. So that is known as Kirchhoff's voltage law. So without further ado, let's just pull up a circuit here and we'll talk a little bit about it. So as you can see here, is the current only has one path to flow all the way through, and it must go through every resistance and return back. So when we look at this circuit and we put an amp meter in it, and it doesn't matter where we put the amp meter, we can put it anywhere. The amp meters are going to be exactly the same if we have current flow through. So I total is the same as I1, same as I2, the same as I3. It doesn't matter where we put our amp meter. Once again, amp meters are connected in series. So a little review: we put them in series with our load in order to determine the current flow. So next, if we're thinking voltages, this is where Kirchhoff's voltage law applies to all circuits, but if we look at it, we have three different volt drops across here. Voltage 2 and voltage 3 across each one of these resistors. So we always connect our voltmeters up in parallel with whatever we're trying to measure. So our supply voltage is 120 volts, and Kirchhoff's voltage law says that if you add all the voltage drops up, it should equal to your voltage rise, or your supply voltage. So if I were to add voltmeter 1, 2, and 3 together, I'll have 120 volts. And so V total, or E, will be equal to V1 plus V2 plus V3. So basically a little recap of Kirchhoff's voltage law. So let's go ahead and we are going to solve for this circuit here. First off, we'll review here to calculate resistance total. Simple, is RT, total resistance, and give us the total opposition and current flow in the circuit. And it's simply adding up the resistors that are in series. So in this case, we've got 30 ohms plus 25 plus 20 ohms. And so that'll come to 75 ohms. Alright, so now that we have the total resistance, we can use Ohm's law to calculate the total current of the circuit. Total would be equal to our applied voltage divided by the resistance total. We got 120 volts divided by 75 ohms, and that will come to 1.6 amps. There you go. So we know the total current, and it's going to be the same no matter where we look on this circuit. 1.6 amps, 1.6 amps, and we can go ahead and calculate the voltage drop. So voltage 1 will be equal to, so voltage 1 would be equal to I times R. So that would be equal to 1.6 amps times 30 ohms. That would come to 80 volts. Voltage 2 would be equal to 1.6 amps times 25 ohms. 40 volts, and voltage 3 is going to be 1.6 amps times 20 ohms. So 32 volts. And if we add up our three voltage drops, this is how we know we did it right. Applying Kirchhoff's voltage law, 48 plus 40 plus 32 comes to 120 volts. And this is pretty much that easy. So, yeah, simple series circuit. So we have to know, review series circuits, and then we're going to review parallel after this. Then when you get to series parallel, it makes it a lot easier. So just one other concept here. So in this circuit, we had 1.6 amps flowing. And if I were to put my voltmeter across one of the resistors, so V2 here, I would get its value, which was 1.6 times 25, 40 volts here. Now if this were to become open circuited or break right there, what would happen is that voltage would rise across the break. And so now we would get the full applied voltage of 120 volts across the open portion of the circuit. No different if we put a switch in somewhere and it was open. I would get the full 120 volts or the applied voltage across that switch. Anyways, hope that helps you review series circuits a little bit. And next video should be parallel.